Hello and welcome to this FP1 exam paper walkthrough. This is the May 2023 paper. It was an hour and a half and you were allowed a calculator and the formula booklet. Jumping straight into question 1. Use the standard results for this and this to show that for all positive integers n, this statement here is true, where a, b and c are integers to be determined. First of all, jump to the formula booklet. Here we are under the FP1 section summations. We're using these two here. So I have just copied and pasted those across. So we need to use these to prove the thing at the top of the screen. So a key point here to begin with is how we can split this up. And what we can do is first of all expand out the brackets. And then we can split the summation. So we can sum r cubed, and then we can do two lots of the sum of r squared. Then we can apply our two formulas that we know. We've got r cubed, that's 1 over 4 n squared n plus 1 all squared, plus two lots of 1/6 n plus 1 2n plus 1. Then it's just a case of making this look like this to find a, b and c, noting that they are integers. So here, a bit of manipulation. Let's leave this for now. And we've got 1 over 3 n plus 1, 2n plus 1. So now we can factorize out n and n plus 1. Do we want to do that? Yes, we do. There we go. And also, let's take out 1 over 12. So from this first term, 1 over 12 n plus 1 will leave us with 3 lots of n plus 1. And from the second term, taking out the same thing, will leave us with a 4 2n plus 1. Now that bit in the big brackets there needs to become a quadratic here. So we're just going to tidy this up and then we will be finished. So this is 3n squared plus 3n plus 8n plus 4. Final line gives us 3n squared plus 11n plus 4, and that is our final answer, where a, b and c are 3, 11 and 4 respectively. Double checking we finished the question. Yes, it was just that one thing to do. On to question 2. Okay, we can't use calculator technology, just emphasizing that you are showing your working out. Given that x equals 2 plus 3i is a root of this equation, write down another complex root of this equation. Two quick things here. Write down and 1 mark are both giving you the clue that you shouldn't have to do anything to figure this out. It should be something that you know. And we know that because complex roots come up in complex conjugate pairs. So if this is a root of the equation, then its complex conjugate is also a root. So 2 minus 3i is the answer to the first one. Now we've got two roots to this equation. So part B, use algebra to determine the other two roots. So we've got 4 in total because it is a quartic. So first I'm going to put into factors the two roots that I've got. So x minus root 1, which is 2 plus 3i, and x minus root 2, 2 minus 3i, times by the other two roots, which I will have as a unknown quadratic in their factors there, must equal 0. Now you don't have to do it this way. What you could do is expand these two brackets in the front here and then divide your quartic equation by that quadratic using a long division. If you want to do it that way, that's absolutely fine. Sometimes I like to do it that way, but this time I'm going to do it by equating the coefficients. So I'm going to expand out the thing I've got here, all of that, and then compare it to this, and that should tell me what a, b and c have to be. So whichever of those two methods you choose to do, you're going to have to expand these two brackets here first. So we've got x squared minus x lots of 2 plus 3i minus x lots of 2 minus 3i plus 2 plus 3i times 2 minus 3i. And all of that is multiplied by this. Tidying this up, x squared minus 2x minus another 2x from the next bracket is minus 4x, minus 3xi plus 3xi from the next bracket disappears, and then we've got plus 4 from the expanding of this double bracket here, plus 6i minus 6i is disappeared, and then minus 3i squared, which is a plus 9. So all of that simplifies quite nicely. And that gives us x squared minus 4x plus 13. And that times by this must equal our equation up here. So I'm going to compare the coefficients to figure out what my missing numbers must be. I'm not going to do all of it though, because I can see straight away x squared here times ax squared, that's the only power 4. So a must be a 2. Otherwise we can't get a 2x to the 4 out of this. In a similar way, jumping to the end, 13 times c is the only constant, so that must equal 39. So c must equal 3. Now I do have to do a little bit of work to find b. I'm going to use the x cubed terms, I think. To get x cubed, we do x squared here times bx here, so that's bx cubed, and then minus 4x here times ax squared here, minus 4ax cubed has to equal minus 8x cubed. But we know what a is 2, that's minus 8x cubed already, which is telling me that b must be 0. That's the only way that can be true. We can double check that if we like by considering, for example, the x terms. So we've got minus 4x times c, which we know is 3, that's minus 12x, and then 0 is what we've suggested here, times 13, so that's 0, so we've got minus 12x, which matches what we've got here. So I'm confident this is right. That means our quartic factorizes into these two quadratic brackets, and of course we've already got the solution from the first quadratic bracket. That was the complex root given to us and the one we found at the very top of the screen there in part A. So the only thing we need to do to find the other two is to solve this is equal to 0. And when that is equal to 0, we've got another set of complex roots, plus or minus I times a root of 3 over 2. That is the solution. We found the other two roots of the equation. Now part C, show all 4 roots on a single Argand diagram. So we've got 2 plus 3i at the top there. And then we had 2 minus 3i, and then we've just found, just at the top of the screen there, these two here. So we're showing all of these 4 on an Argand diagram. This is the real axis, this is the imaginary axis, so we want 2 here, 3 or 3i here, so this is one of them, minus 3 or minus 3i here is the other one for the first two, and then the second two are on the imaginary axis, say here at root 3 over 2 or root 3 over 2i, and here minus root 3 over 2 or minus root 3 over 2i. Some people like to include the I on the imaginary axis. Some people say you don't need to because you've already got the fact that it's imaginary up on the top there. That's part C finished, and that's question 2 finished. Question 3. The rectangular hyperbola H has Cartesian equation xy equals 9. The point P with coordinates this, where t is not 0, lies on H. Use calculus to determine an equation for the normal to H at the point P. So we're going to use calculus because to determine the equation of the normal we need the gradient. To find the gradient of the normal, we first need the gradient of the tangent. To do that, we're going to differentiate. So there's our calculus right at the start, is differentiating this. I'm going to use implicit differentiation, and so I will need the product rule. That means differentiate the x and leave the y, and then leave the x and differentiate the y, which we can't do with respect to x, so I need to write dy by dx to show that differential there. Now I can, put 9. 9 differentiates to 0. Don't make that mistake in your exam. Now I can rearrange, and dy by dx is equal to negative y and then divide by x, like this. At point P, we've got the coordinates, so we know what x and y are at that point. So the gradient, let me call it m1 of the tangent at P, is equal to the y coordinate, which is 3 over t, negative 3 over t, divided by the x coordinate, which is 3t. That simplifies to minus 1 over t squared. Now that's the gradient of the tangent, but we want the normal. So now we need to use m1, m2 is equal to minus 1. So the gradient of the normal is minus 1 divided by minus 1 over t squared, which is t squared. Usually I would continue working down the page, but let me jump up to the right here to keep it all on one screen. At this point, we know the gradient of the normal, so we are going back to the line equation, y minus y1. y1 here is 3 over t, the y coordinate of P, is equal to the gradient, which we just found was t squared, times x minus x1, and x1 in this case is 3t. Now that is the equation of the normal. However, they specifically want it in this form here, where we have t times y. So I need to multiply everything by t. That will get me ty minus 3 is equal to t cubed x minus 3t. And then it looks like we're going to need to expand the bracket and bring the y and the x together on the left. So ty minus 3, t cubed x minus 3t to the 4. So ty minus t cubed x is equal to 3 minus 3t to the 4. Now it's in the correct format. If you really wanted to be nice and formal, you could stick on the end here, f of t is 3 minus 3t to the 4. Make the examiner smile. That's part A finished. Part B, given that t is equal to 2, determine the coordinates of the point where the normal, this thing we've just found, equation of the normal here, meets h again. Where it meets h is where this and the equation of h are solved simultaneously. So for part B, t is equal to 2, so I'll put that in straight away. That gives us 2y minus 8x is equal to 3 minus 3 lots of t to the 4, 16. So that's minus 45. 2y minus 8x is equal to minus 45. That's the equation of the normal. We also know that xy is equal to 9 for the entire curve h. So we need to find where these two meet. And keep in mind, we do know one of the coordinates where these two meet. We know that they meet at P. So that's 3t, 3 over t. And that's P. And we know now that t is 2, so that's coordinate 6, 3 over 2. So this is one of the solutions. What we need to do is find the other one. To do this, x is equal to 9 over y, and substitute that in to the other equation that we've got. So 2y minus 8 lots of x, so that's 72 over y, equals minus 45. Rearrange this, we get 2y squared plus 45y minus 72 equals 0. Now to factorize this, I can be sneaky and I can say I already know one of the answers. One of the answers for y is 3 over 2. So that would come from the bracket 2y minus 3. So one of my brackets is 2y minus 3, and that will make it easier to find the other one, because to get 2y squared, that must be a y, and to get minus 72, this must be a plus 24. Double check it works for the 45. 2, 24, that's 48 minus 3, yes, 45. So the other solution is minus 24. And this is the one that we already knew. So if y is equal to minus 24 and x is equal to 9 over y, 9 over 24, that's 3 over 8. So the coordinates of the other point is 3 over 8 minus 24. Let's double check we've finished that question. Yes. Question 4. The transformation represented by A transforms triangle T to triangle T prime. The area of triangle T prime is 3 times the area of triangle T. Determine the possible values of K. Here, K is a constant. The important thing here to realize is that the scale factor, 3 times, is the determinant of A. The determinant of A is minus 3 times K, minus 8 times minus 3, so that's minus 3k plus 24. Now that must equal 3, but not only 3, and there is a little clue here in the question. Determine the possible values, plural. That's because this could be 3 times with a positive 3, or it could be 3 times with a negative 3. If you remember your transformations, positive 3 is 3 times bigger on one side of the centre of enlargement. Negative 3 is still 3 times bigger, but on the other side of the centre of enlargement. So it doesn't matter if this is negative 3 or positive 3, it just needs to equal one of those. So it's either 3 or negative 3. If it's negative 3, we get negative 27, and k is equal to 9. Or negative 21 here, then k is equal to 7. So these are our two solutions for part I. That doesn't seem like a lot of work for 4 marks, but you're getting 1 for realizing that you need to use determinant of A. You're getting 1 for correctly equating that to 3 or negative 3, and then you're getting 1 for 7 and 1 for 9. Part B, or II I should say. B, the matrix, is equal to A minus 4, 2, 3, and BC is equal to this, where A is a constant. Determine in terms of A the matrix C. So a little bit of matrix algebra here. If we know BC is equal to this thing, 2, 5, 1, 1, 4, 2, and then we can multiply on the left of this the inverse matrix of B, like so. Then that combines with the B to make I, and I, the identity matrix, has no impact on C, so this thing here, I won't keep writing out all the numbers, but that thing there is equal to C. So if I want to find C, then I need to do the inverse matrix of B times by this matrix that we've been given in the question. To find the inverse matrix of B, I need to do 1 divided by the determinant of B times by 3a, they switch places, and this becomes the negative of what it was, 4 and a minus 2 there. The determinant of B is, that's 3a minus 4 times 2, that's 3a plus 8, that's quite an awkward determinant, 1 over 3a plus 8 times 3, 4 minus 2a. Now you could put that fraction inside the matrix, but it's just adding a lot of fraction work to what you're going to write. What I would suggest is you just leave that in front, 3a plus 8, 3, 4 minus 2a, and then apply that matrix onto the one I was too lazy to write out all those times. So that stays in front, and then we've got 3 times 2 plus 4 times 1 is 10, 3 times 5 plus 4 times 4 is 31, 3 times 1 plus 4 times 2, that's 11, and then the second row, minus 2 times 2 plus a times 1, minus 4 plus a, or a minus 4, then we've got minus 10 plus 4, a, and then minus 2 plus 2a, and that is our matrix C. And again, you could put that determinant inside, but it's just going to be a lot of fraction writing. I think it would be fine to leave it in front like that. Part B finished. On to question 5. The equation above has roots alpha and beta. Without solving the equation, determine the value of this thing here. Okay, the key point here is to realize that if your root is alpha and beta, then like we did on one of the previous ones, we can put those into their factorized brackets like that, and that has to equal the equation. What that means is alpha times beta must equal this constant on the end, and alpha plus beta must equal this negatived, so the 6 there. The rest of the question follows on from these two things. We need to be using alpha beta and alpha plus beta. So in part A, what we need to do is manipulate this expression into alpha beta and or alpha plus beta here. And then we can replace alpha beta with 3 and alpha plus beta with 6. To do that, just start by expanding it. So we've got this plus alpha squared plus beta squared plus 1. I hope you can see that alpha beta is already there. Squared, that's great, we know what that is, that's 3 squared. Alpha squared plus beta squared we can get by thinking about alpha plus beta equals 6 and then squaring this expression. So if I square this and square this, we get alpha squared plus 2 alpha beta, which we know alpha beta, plus beta squared is equal to 36. Alpha beta we know from this one is 3, so this middle term is a 6. So alpha squared plus beta squared must be 36 minus 6, which is 30. So alpha plus beta squared is 30, we still have a plus 1 on the end, and alpha beta we know is 3, so this is 3 squared, which of course is 9. Add those together, we get 40 for part A. Part B is very similar. If we know that these are the roots, then to get the quadratic, what we would normally do here is to have x squared minus root 1 plus root 2, what we've called alpha and beta so far, plus root 1 times root 2. Now I haven't used alpha and beta because we're using that to mean something else. So this thing here is x1 in that little expression there, and this is x2 in that little expression, but that's not really what we need. What we need is to be able to manipulate these expressions by adding them together and using these expressions here to get a number. What would this number be if we add this root and this root together? And what would the number be over here if we multiplied this root by this root? So we're going to do that. We're going to add these expressions and multiply these expressions, and then use the fact we know alpha beta is 3, alpha plus beta is 6, to find out an actual numerical answer. So we've got alpha over alpha squared plus 1 times beta over beta squared plus 1, and that is just alpha beta, alpha squared plus 1, beta squared plus 1, and now we're using not just the bit given in the question, but also part A, because if you see the expression we've got here in the denominator, this is this thing that we found in part A. So we know that the denominator is 40, and from the original question up here we know that alpha beta is 3. So the multiplication of these two roots, i.e. the constant on the end of the equation, is 3 over 40. Now if we add these two roots, alpha over alpha squared plus 1 plus beta over beta squared plus 1, so we're going to need alpha beta squared plus 1 plus beta alpha squared plus 1, all divided by these two multiplied together. And again, we know what that is, that's 40. So on the top we've got, if I expand that out, alpha beta squared plus alpha plus beta alpha squared plus beta, all divided by 40. And then here, this is alpha beta times beta. So I can write that as 3 lots of beta, because we know alpha beta is 3, again coming all the way back up to the top there, plus an alpha, And then same here, we've got alpha beta times by alpha. So this is a 3 alpha plus beta. Now I can add those together. This is still divided by 40. That gives me 4 lots of alpha and 4 lots of beta. So that's alpha plus beta over 40. And again, we know alpha plus beta, if we go all the way back up to the top, alpha plus beta is 6. So that is 4 times 6 over 40. That's 6 over 10, 3 over 5. So the summation of these two roots, which is this part of our quadratic equation, 3 over 5. So the quadratic equation, which has roots given in part B, is x squared minus, don't forget that minus there, 3 over 5x plus, what was it, 3 over 40. But be careful, because it's an equation, first of all, and also we need p, q, and r to be integers. So I'll make this equal to 0 for an equation, and then multiply everything by 40. So we've got 40x squared minus 24x plus 3 is equal to 0, where p is equal to 40, q is equal to minus 24, and r is equal to 3. And that is the end of the question. Yes. On to the next. In this question, you must show all stages of your working. So again, you can't use your calculator too much here. It's emphasizing they need to see your working out. Part A, determine the exact value of the magnitude z1 plus z2, which is the magnitude of 3 plus 2i plus 2 plus 3i, which is the magnitude of 5 plus 5i, which is applying Pythagoras, 2 times the square root of 5. Given that omega, or w, is z2, z3 over z1, determine w in terms of a and b, giving your answer in the form x plus iy, where x and y are real numbers, but not necessarily integers. Okay, z2 is 2 plus 3i, and z3 is a plus bi. 2 plus 3i times a plus bi, brace yourself for a lot of algebra here, divided by z1, which is 3 plus 2i. Okay, what I'm going to do is expand the brackets on the top and then multiply top and bottom by the conjugate of z1 in order to get rid of the imaginary part on the bottom in the denominator, so that we can split the fraction into real and imaginary parts later. So the first thing, multiply out that numerator. 2a plus 3ai plus 2bi minus, because of the I squared, minus 3b. All of that divided by 3 plus 2i, and then multiply by 3 minus 2i top and bottom, which we can do because that's just multiplying by 1, but the effect of that in the denominator is to have 3 times 3, 9, minus 6i plus 6i, which disappear, and then minus 4i squared, which gives us plus 4. So we are making the denominator a real number. Unfortunately, that has quite a lot of algebra on the top. So we've got all of these things here, multiplied by 3, so that's 6a plus 9ai plus 6bi minus 9b, and then they're all multiplied by minus 2i as well, minus 4ai minus 6ai squared, so plus 6a, minus 4bi squared, so again that becomes a plus 4b because the I squared becomes a minus 1, and then plus 6bi. Simplifying all of this, 6a and 6a, that's 12a, minus 5b plus 5ai plus 12bi. All of that is divided by 13. Refresh my memory what we're trying to do here, in the form x plus iy. So we need to split this into real and imaginary parts. So we've got 12a minus 5b divided by 13 plus I lots of 5a plus 12b divided by 13, and that's our x plus iy that we need here, where x and y are real. If we really wanted to finish it off, that means x is 12a minus 5b over 13 and y is 5a plus 12b over 13. Okay, part B finished. Given also that w is equal to 4 over 13 plus 58 over 13i, determine a and b. So w is 4 over 13 plus 58 over 13i, and keep in mind what we just found in part B is also w, so that is equal to this thing here. So we can equate the real and imaginary parts to get 4 over 13 is equal to 12a minus 5b over 13, and 58 over 13 must equal 5a plus 12b over 13. We can get rid of all the fractions. 12a minus 5b, 58 5a plus 12b. Then I'm going to multiply the first one by 12 because that gives a smaller number here. 144a minus 60b. Multiply this one by 5. That's 290. 25a, and what we needed 60b, so we can add these two equations together. 338 169a, which is nice because that means a is equal to 2, and if a is equal to 2, then we can find b. B must equal 4. Okay, a and b found. That's part C finished. Part D. Determine the argument of w, giving our answer in radians to 4 significant figures. Okay, the argument of w is equal to the inverse tan of the imaginary part, 58 over 13, divided by the real part, 4 over 13. Grab yourself a calculator, make sure it's in radians, and you should get the answer 1.5019 ... and they wanted it to 4 significant figures. 1, 2, 3, 4. That is the end of the question. Yes, so on to the next. Question 7. Show that the equation f of x equals 0 has a root alpha in the interval 1, 2. Okay, what we're doing here is we're going to find f of x at these two and show that there is a change of sign. So if we have f of 1, that's 1 to the 3 over 2, that's 1, plus 1 minus 3 is minus 1, and f evaluated at 2 is something more decimally, 1.8284 ... Okay, now there are some key terms and phrases you need here. First one is that f of x is continuous, it's a continuous function, and there's a change of sign. That's your second phrase that you need, a change of sign. Therefore, there is a root in the interval that we've just used, i.e. 1, 2. Part B, starting with the interval 1, 2, which we've just got, use interval bisection twice to show that alpha lies in the interval 1.25 to 1.5. Okay, we're using interval bisection, so find the midpoint. 1 plus 2 divided by 2 is equal to 1.5. So evaluate at 1.5. And that is equal to 0.337 ... Now that is a positive number, So that replaces the 2. It's a smaller positive number than when we evaluated at 2. So we know now that the interval is 1 to 1.5. Now 1 plus 1.5 divided by 2 is 1.25. So the midpoint again. This is interval bisection. You're always taking the midpoint of the two that you know. The root is between. So evaluating at 1.25. And that is equal to minus 0.352 dot dot dot. So that is a smaller negative number than when we evaluated at x equals 1. So that replaces the lower boundary. Therefore, our interval becomes 1.25 to 1.5 as they said it should. Part C, determine the derivative of f of x. So part C, if f of x is equal to x to the 3 over 2 plus x minus 3, then the derivative is 3 over 2 x to the 1 over 2 plus 1. That's the first part done, and then we're going to use that, yes, in the Newton-Raphson process. So they're telling us the first approximation, 1.375. And we need to find just a second approximation to 3 decimal places. So we're only doing it once. If you forget the formula, it is on your formula booklet. Here it is, just underneath the summations. I'll copy that across. So this tells us the next one. So x2 is equal to x1 minus f evaluated at x1 over f prime evaluated at x1. So that's 1.375 minus the function evaluated at 1.375 divided by the derivative evaluated at 1.375. So the function there gives minus 0.0126 dot dot dot, and the derivative 2.758 dot dot dot. And if you keep your accuracy on your calculator, you get 1.3795 dot dot dot, and to 3 decimal places that's 1.380 for our second approximation. That is the Newton-Raphson question finished. Linear interpolation. Okay, for linear interpolation we've got a little formula. Let me put it here. B minus x1 over x1 minus a is equal to the function at b divided by the function at a. Back up to the question. 1.25 to 1.5. So this is our a and b, and x1 is our approximation. So 1.5 minus x1 over x1 minus 1.25 is equal to the function evaluated at b and a. But if you remember where this comes from, we're looking at something on the graph where here is the root, and then we've got the point here from this one, and maybe the point here from this one. We're making similar triangles, and where this formula comes from is that this f of b and this f of a are the ratio on the right hand side of my equation, and then this bit here and this bit here form the ratio on the left of the equation. So we don't need to worry about negatives. More to the point, we should not take a negative for this part here. We're looking at the distance. So although one of these definitely will be a negative, in fact I think we've got these. Didn't we already have these? 1.25. 1.25, here it is, minus 0.352 is actually 0.352 in this case, because it's a distance, so we don't want the negative. And then did we have 1.5 as well? We did, 0.337. Of course I'll have to do that on my calculator again to maintain the accuracy, but I can show all of the algebra with these numbers before I do that. So we've got 1.5 times that number minus x1 times that number is equal to x1 times this number minus 1.25 times this number. 1.5 times 0.352 plus 1.25 times 0.337, and then bring the x1s together and factorize and then divide. We end up with this number plus this number. And getting all of the accuracy back on my calculator there and putting it all in one big calculation, it gives me 1.37778 ... to 3 decimal places, I think it was. Let me just check that. Three decimal places. Okay, there we go. That seemed like a lot of work for that question. We did about 4 different methods there, but we are finished. On to question 8. The point P lies on the parabola with the equation y equals 8x. Remember, we're using this form. So immediately that's telling us a is equal to 2. Show that the point Q also lies on this parabola. So we're just putting that in. Y squared is equal to, I'm actually going to put the y in, here's the y. So we've got minus 4 over p squared is 16 over p squared. And then the other side of the equation, 8x is equal to 8 times 2 over p squared, which is also 16 over p squared. Therefore, y squared equals 8x is true. Let me write it like this, just really trying to make sure the examiner knows that I know what's going on. True. Part B, show that the chord PQ passes through the focus of the parabola. Now the focus of the parabola is either plus or minus a 0, and we know a is 2, so plus or minus 2, 0. To do this, I'm going to find the equation of the chord PQ, and I can do that just by finding the equation between 2 points. So we need the gradient first, and then into a straight line equation. So part B, P is 2p squared 4p, and Q, we've got on the screen here, 2 over p squared minus 4 over p. So to get the gradient, we've got y2 minus y1, x2 minus x1, minus 4 over p minus 4p over 2 over p squared minus 2p squared. That does not look nice, but let's manipulate it a bit. If I multiply everything by p squared to get rid of the fractions inside fractions, we get minus 4p minus 4p cubed over 2 minus 2p to the 4. Now I can cancel some of those numbers and start to factorize. So in fact, let's cancel the negatives as well. So I'll do that first. That gives me 2p plus 2p cubed over p to the 4 minus 1. Now I can factorize 2p 1 plus p squared, and in the denominator is the difference of 2 squareds, p squared plus 1, p squared minus 1, that's gone. So we get 2p over p squared minus 1, which still isn't great, but it's a lot better than it was. So that's our gradient m. Now we can use one of the points. I'll use p to avoid those extra fractions. We've got y minus y1, that's 4p, is equal to the gradient 2p over p squared minus 1 times x minus x1 is 2p squared. Now that's the chord PQ, and what we're trying to do is show that that goes through the focus, 2, 0 or minus 2, 0 of the parabola. So the focus has y equals 0. So let's put that in. 0 minus 4p, 2p over p squared minus 1, x minus 2p squared. So I'll multiply by p squared minus 1 on the left, so get minus 4p cubed plus 4p. And then on the right, we've got 2px minus 4p cubed as well. So that cancels with that. And then we've got 4p equals 2px. And that gives us x equals 2. Therefore, the focus is 2, 0, as expected. Because we knew up here that the focus should be that. Part C, the tangent to the parabola at P and the tangent to the parabola at Q meet at the point R. Determine in simplest form the coordinates of R. Okay, so we need the tangents at these 2 points and then solve them simultaneously. To get the tangent, we need the gradient by differentiating the curve. So we've got y squared is equal to 8x, differentiating this implicitly, 2y dy by dx is equal to 8 dy by dx is equal to 4 over y. Now we need the coordinates for p and q again. So at p, the gradient is 4 over y becomes 4 over 4p, 1 over p. Putting that into the line equation, y minus y1 is equal to the gradient times x minus x1. For q, same idea, but the gradient now 4 over y becomes 4 over minus 4 over p, which is minus p. So the straight line equation on this becomes y minus or plus 4 over p is equal to the gradient minus p times x minus x1. Now we need to find where these two meet. So we are solving them. So I'm going to make y equals on both and then make them equal to each other. And over here, now where these two meet must have the same y, so we can put them together. 1 over p x minus 2p squared plus 4p must equal minus p x minus 2 over p squared minus 4 over p. Solving this, I'm going to multiply everything by p, get rid of those fractions. X minus 2p squared plus 4p squared is equal to minus p squared, expanding out the bracket as well, plus p squared times 2 over p squared is just 2, minus 4. Collecting the x's together, x plus p squared x is equal to 2 minus 4 is minus 2, and another minus 2p squared. Factorizing 1 plus p squared minus 2, 1 plus p squared. That's very nice. We get x is equal to minus 2. I expected something dependent on p, but I'll assume that's okay. Now we know what x is, we can put it back in to find y. So I'll choose the one over here on the left to do that. So y is equal to 1 over p times x, which we now know is minus 2, minus 2p squared plus 4p. I guess we could tidy this up a little bit. Let's put it into a single fraction at least. Minus 2 minus 2p squared over p plus 4p squared over p. So then we can add those p squareds. 2p squared minus 2 over p. So the coordinates of point R is minus 2, 2p squared minus 2 over p. And I think that is finished. It wanted it in its simplest form. I think we did that. On to question 9. Proof by induction. Of course, couldn't get away with it. Okay, proof by induction, 4 standard steps. We want the basis step, which is just to prove that it is true for the number that we're given. The base number, in this case 2. We're going to start at n equals 2. So 4 to the 2 plus 6 times 2 minus 10 must be divisible by 18. That's 16 plus 12 minus 10 is 18. Obviously 18 is divisible by 18, so it is true for n equals 2. That's our basis step. Now we need to make an assumption. We're going to assume that it is true for n equals k, so that's 4 to the k plus 6k minus 10 is divisible by 18. That's what we're assuming. And now the induction, which should use that assumption at some point. So at this point what we're trying to do is prove that it is true for k plus 1, assuming it's true for n is equal to k. So we're going to use f of k plus 1. If you want to use a function notation, that's okay. 4 to the k plus 1 plus 6 times k plus 1 minus 10. Now a few ways you can approach this. You can do the function of k plus 1 minus the function of k. That will probably work in this case. What I'm going to do is try to manipulate the expression here so that it's some multiple of the function of k. So first of all, let's split this index here. This is 4 times 4 to the k. That's what that means. Expand the brackets. 6k plus 6 minus 10. So we've got 4 lots of 4 to the k plus 6k minus 4. Now because of the 4 multiplier in front here, what I'm going to do is I'm going to force these two into 4 times these two. Because if I can get 4 times this and 4 times this and 4 times this, then it's 4 times something I know is divisible by 18 that is also divisible by 18. So to do that, I'm going to just manipulate this a little bit. This one's already there. What I want is 4 lots of 6k, so I really want here is 24k, but I can't just put that in. It's not 24, it's 6. So to keep this line equal to the previous line, I need to subtract 18k there. So 24k minus 18k is still 6k. So I haven't changed anything, although I've got the 24k that I need. I'm going to do something similar here. I want 4 lots of minus 10, so I'm going to force this into minus 40, but what it actually is minus 4. So to keep that minus 4 true, I need to add 36. So I hope you can see that this line is still equal to the previous line. The reason for doing that is that I've got 4 lots of 4 to the k plus 24k minus 40, and all of that is 4 times the function of k, which I know is divisible by 18. The consequence of doing that is that I have to have minus 18k plus 36 on the end, but that's okay because I can see quite clearly that that also is divisible by 18. So what I can write here is that this is 4 lots of 4 to the k plus 6k minus 10 minus 18k plus 36, which is 4 lots of f of k. And then to really emphasize that these two are divisible by 18, let me write plus 18 lots of 2 minus k, like that. So here our assumption step comes into play. We've assumed it's true for n is equal to k, so if this thing here is divisible by 18, then we've shown that f of k plus 1 is also divisible by 18. And that's because this obviously has a factor of 18 in it, and you can see clearly that this also has a factor of 18. Don't stop there though, we need a conclusion step, which has all the writing. We've said it's true for n equals 2. If true for n equals k, then we've proved that it's true for n is equal to k plus 1, and because we know it's true for 2, and then let's say k is 2, it must be true for 3, that's what we've proven there, and now if we know it's true for 3, it must be true for 4, and so on and so on and so on. therefore true for all integers where n is greater than or equal to 2. And that is the question finished. That's also the end of the paper. Hopefully that has been useful for you.